So, what are power law networks? Let us first look at the degree distribution of real world networks. This is a network of Facebook pages with mutual likes, and look at it. So, you have lots of pages with very few likes, but then you have a handful of pages which are like super popular, and this is a network of citations. Here you see that lots of nodes have very little citation, but there are a few nodes, few papers which have a huge number of citations. Right. So, you see that the degree can be like several fold different for the max connected node and the other nodes. And here you have a neuron connectome in Drosophila, and you see again that you can have very high degrees. So, you have very low degrees on the one hand and much higher degrees on the other hand. Okay, and this is another worm network. This is another worm network where you again have massive fluctuations in degree. So, the highest degree by the lowest degree is something like 750, right, or even higher than that. So, you have hugely skewed degree distributions, okay, and these are the kind of real world networks that you have, and when you have such real world networks with such skewed distributions, they are not captured by small world. So, this is not the kind of degree distribution that you see in small world networks. So, how do you fit this degree distribution? Enter power laws. So, there is a power law degree distribution that you see for these kinds of real world distributions. Now, this is how the power law degree distribution looks like. So, you have P of k, the probability of observing a node with degree k is proportional to k to the minus gamma. And very interesting, you can actually generate these networks by using a what is known as a preferential attachment model or rich get richer model. You can rationalize that because this is typically how wealth distribution looks in the society. Right? You have a few people that are really rich, you have a few people who have a lot of wealth, and a lot of people have very little wealth. Okay? There is a very skewed distribution in terms of the richest person to the poorest person. That is not what you see in like a small world network or something like that. A small world network is typically more egalitarian, right. So, there is some fluctuation in the number of edges, but the max degree by min degree would be much smaller in a small world network compared to what you would, or a random network for that matter, compared to what you would see in a power law network. Okay. So, how does the rich get richer model work? The model is very interesting. So, you start a network with just two nodes. Now, you have a third incoming node that can connect to either of these two nodes, and this connection is going to be made based on the degree of the existing nodes. So, higher the degree of an existing node, greater the probability of an incoming node to connect to it. Here now it is no different, both nodes have the same degree of 1. So, let us say this connects here. And now when you have the next incoming node, it is going to connect to the middle node with higher probability. So, maybe this is the most likely outcome. Of course, it had some probability of connecting to the other nodes as well. So, you can occasionally have connections like this. So, if you see over a period of time how this network evolves, you will have certain nodes that start having very high degrees and many other nodes just being peripheral with low degrees, whereas these nodes have very high degrees. So, what you have are hubs and resources. You can think of them as resources or whatever, but the most important terminology here is that of hubs. you have certain nodes that are very highly connected and turn out to be hubs. And this has implications for how robust these networks are and things like that as well. Okay. So, when you generate networks using this model, like you start off with a network with just 2 nodes connected by a single edge, and every incoming node makes one edge to one of the existing nodes. In fact, you will see that there is there is no clustering at all in this kind of a network, right, because there is no opportunity for a triangle to form. So, the clustering will be 0, which is not a necessary feature of power law networks. It is just one aspect of how, it is just one way that these networks can be created. There are other ways to create. So, if you have multiple edges that can be formed for every entering node, then you will have a fair degree of clustering and so on. So, clustering is in fact an important feature of real world and power law networks, although this model, this simple, very simple model that we talked about does not exactly capture that. So, the networks generated by this model have a power law degree distribution characterized by gamma equal to 3, and typically scale free networks with 2 less than gamma less than 3, right. So, gamma in the range of 2 to 3 is commonly observed in very many biological networks. They are very small, meaning very short path lengths, and the characteristic path length is as low as log n. Log n is already a small quantity, and log n is going to be a much tinier quantity, and which is much significantly smaller than random networks as well. So, if you see, this model seems to be much more complete. It is able to capture various aspects of real world networks in terms of low path lengths, high clustering, as well as the skewed degree distribution. This skewed power law degree distribution is very interesting and arises in many scenarios. So, this power law distribution is this skewed degree distribution that you see in the power law is also common to many other world life scenarios, which we will look at shortly. But before that, let us recap the preferential attachment model. Many real networks grow, right, could be citation networks or a protein network in yeast or the World Wide Web and so on. And the key underlying principle here is that new nodes attach to existing nodes in a preferential fashion, meaning they do not attach at random, but they attach based on the existing degree of the network and so on. And this probability can be computed as what is the current degree of the network by the sum of total degrees in the network. So, higher this number is, so this is literally degree centrality, right, the normalized version of degree centrality that we talked about in the previous class. So, here Pi is the probability of attaching to node I and Ki is the degree of node I, and you sum all the degrees. So, an arrival node is going to connect to a node with, suppose the existing nodes had these kinds of degrees, right. So, 8, 4, 2 and 1 which sum up to 15. So, a new node arriving in the graph is going to most likely connect to the first node with a probability of more than half, to the second node with a probability just over a quarter, or the third node with a probability of 2 by 15, or only a 1 in 15 probability of connecting to the last node with just a degree of 1. So, this is a sort of fictitious example. So, you cannot have degrees of 8, 4, 2 and 1 in a network with no other nodes, right. Just to give you an idea of how the existing degrees of in the network will skew the probability of how a new arriving node connects to the existing nodes in the network. So, the question is, which of the following distributions follow a power law? Right. So, could it be the number of views for YouTube videos, book sales and populations of cities and so on. Okay. So, now let us look at the power law distributions that was the subject of the previous question, and you also find in many real world scenarios. So, what is this power law distribution? We know that heights of humans follow normal distribution. What would happen if it were a power law distribution? Right. So, what you see on the left is a normal-ish distribution, and what you see on the right is a skewed power law distribution. So, what is a power law distribution characterized by? It is characterized by what is called a long tail. So, it does not die off. right? You have a longish tail, and in the context of degree distribution, suppose you had a log plot, you will get a roughly linear line like this. You can think of that, right? Because you're saying that n, or you can think this is p as well. So p is basically k to the minus gamma. So log p is going to be a linear line with so this slope is going to capture gamma and so on, right? So coming back, if you had human heights following a power law degree distribution with a mean height of 5'8", we will have 1.3 million people with height less than 2 feet, and you will also have people with a population that's much higher than skyscrapers. So, which is really unusual, right? So, these kind of distributions, we obviously do not see it in height, but we do see it in other kinds of distributions. So, let us look at the distribution of deaths due to terrorist attack, right? These follow a power law distribution because you have most attacks that affect a very small number of people, however unfortunate they are, but you have a few attacks that unfortunately affect a very large number of people, right. So, if deaths due to terrorist attacks follow a power law distribution, a rare event like 1 in a million will have about 800 deaths, whereas if they were normal, even a rare event would have something like 50 deaths. So, clearly this is not the kind of distribution that we see. So, there are certain real world entities that follow a very unique distribution, which is this power law distribution. So, we normally belabor the normal distribution in school and so on. So, you are very familiar with the normal distribution, bell curve and things like that, but you should now at least commit to memory that there is this other distribution that is very widely observed in the real world, which is this power law or a skewed distribution with a long tail. And a long tail essentially means that you have certain very low probability but still finite probability, right, events of very different size. So, they could be a terrorist attack with a very disastrous outcome, or they could be like an important hub in a protein interaction network with a huge number of connections to other proteins in the network. Another very interesting thing is the Zipf's law, which was proposed by Zipf long ago. This is used to model distribution of word count in documents, and the rank of a word times its probability. So, the rank of the word in terms of its count in a list is times its probability of appearance in the document is roughly a constant. And here basically this is a power law with an exponent -1, and you can imagine, right. So, there are words like the, of, to, and so on, which occur very often in an article or any corpus of documents, and there are other words which are rarer. Most words will be rare, right. So, that gives you the other end of the power law distribution. Most words will be rare, but a handful of words will have very high frequencies like you see in this picture. So, note that the value of R into PR is close to 0.1 in most cases. So, this is another very interesting book written by Barabashi, who was one of the authors of this power law model. So, this power law model was proposed by Barabashi and Albert in 1999. So, it is also called the Barabashi-Albert model of preferential attachment. So, we have essentially seen three different network models today. The first one was the Erdős-Rényi random network model, and then we looked at the Watt-Strogatz small world model proposed in 1998, and then we thirdly looked at the power law distribution and the power law network models, which capture most properties of real world networks in terms of the degree distribution, clustering and low path lengths. So, if you looked at random, it captured only low path lengths. If you looked at small world, it captured both short path lengths and clustering. And if you look at power law, they capture all features in terms of low path lengths, high clustering and also the degree distribution itself. And this book captures very interesting aspects of power law networks and how many real world networks can be modeled or follow power law and what implications it has for attack tolerance or random node failure and so on. Okay. So, a quick comparison between small world and power law networks. So, small world networks are egalitarian, as I was mentioning. There is similar resources that every node has access to, whereas in power law you have certain hubs which have access to several other nodes, then most nodes have access to only one or two nodes. This is how the degree distribution looks like. And small world networks, we typically do not model growth, whereas in power law we model growth through preferential attachment and so on. And small world networks are characterized by local clusters and distant links, whereas in power law the main defining characteristic is this highly tailed, long tailed distribution which follows a power law or a linear plot in a log-log or a linear graph in a log-log plot. And small world networks, we will talk about this in the next class. Under attack it deteriorates slowly, whereas power law networks are very stable under random failure, under random attack. So, we normally talk about random failure and coordinated or targeted attacks. In the case of coordinated or targeted attacks, small world networks, there are no particular targets, no node is so special. So, it is not so much disintegration that you will see. But that does not mean that small world network is superior, because already the connectivity was relatively inferior in some sense to a power law network. But here under targeted attacks, a power law network can collapse very fast. So, this is a vulnerability of power law networks, and this has very interesting concepts that are tied to robustness. So, I will not talk a little bit more about it in this course, but robustness is an important feature of biological systems, and you see that power laws underlying robustness often capture some sort of conservation, right. So, the total amount of robustness is constant. So, you make some part of the network like really strong, it would be at the expense of another part of the network which becomes very weak and so on. It is a very interesting concept that is connected to something known as highly optimized tolerance and things like that, but I will not talk about all of this right now. And in both small world and power law networks, you have small average node to node distance. This is the key feature of both these networks, and which mirrors real world networks very well. Okay. So, that is about what I wanted to cover today. So, we have overviewed key network models that are useful in understanding, classifying and predicting what happens to a network. So, they have all different degree distributions. So, these three different kinds of networks also had different degree distributions, real world networks captured by the Barabasi-Albert model. So, with this we come to the end of various studies on network structure and network models, and we will catch up again in the next class, where we will talk about further aspects of graphs in terms of their motives and other interesting properties.